Let's take a look at some more limiting reactant problems. I have two problems here, each with several parts we can look at. You can read the questions there, hit pause if you need more time. And I'm going to go ahead and go through each one of these 5A, B, and C, as well as 6A and 6B. So I'm going to go ahead and get started. The first thing we would need to do on this question number 5 is start with a balanced chemical equation. So I went ahead and added the coefficient of 2 here, and 3 here, and 4 here. And of course there's an understood 1 here. You don't need to actually write that in. So, and I'll balance the second one down here. 4 sodiums to balance the 4 sodiums over here. Notice the coefficient 2 makes this 4 sodiums. I have 2 oxygens here, and I now have 2 oxygens here. So now I'm ready to go. Okay, so here we have question number 5. You can see part A, find the number of liters of water produced. So I'm trying to find the number of liters of water produced. So underneath my water, I'm going to write X liters. And it's produced at STP. STP means standard temperature and pressure. That's usually code for the teacher telling you you're going to use 1 mole equal 22.4 liters. Now, realistically, this problem doesn't make any sense. You can't find the volume of a gas at STP because water is not a gas at 0 degrees Celsius. But nevertheless, we'll work it just to kind of see how it would work. Okay? Now, we're told here that we have 400 grams of N2H4. So I'm going to write that under the N2H4. And we have 900 grams of N2O4. So I'll write that underneath. Now, I'm going to use what I've described earlier as method 2, where I convert whatever I'm given, in this case grams, of each reactant into moles, and I'll do that first. So I'm going to divide the 400 grams by the molar mass of N2H4. Each nitrogen weighs 14 grams. 2 times 14 is 28, plus 4 is 32 grams per mole. So if I take 400 divide by 32 grams per mole, I will find that I have 12.5 moles of N2H4. I now need to do the same thing to the N2O4. I have 2 nitrogens, each at 14, that's 28 grams, and I have 4 oxygens, each at 16 grams, so that's an additional 64 grams. Adding those two numbers up, I get the molar mass of N2O4 to be 92 grams per mole. So if I take 900 divided by 92 grams per mole, I will get 9.78 moles of N2O4. Now, at this point, we have to pay attention to the coefficients. Notice that we need double the number of moles, 2 moles of N2H4 for every 1 mole of N2O4. So the little trick that I do is I take the moles of each reactant that I have, and I divide by the coefficient in front of it. So there's a 2 in front of the N2H4, so I'm going to take 12.5, divide by 2, and I will get 6.25. That's just a number for a reference. What will I have to divide the 9.78 moles of N2O4 by? If you said 1, because there's a 1 understood in front of the N2O4, that's correct. So that gives me 9.78. Now, by looking at the number 6.25 and 9.78, clearly 6.25 is a smaller number. What this means is that the moles of N2H4, that's my limiting reactant. So because it's limiting, I'm going to only have to focus on the N2H4 moles of limiting reactant. So I'm going to ignore all of this other information. I did that just so that I could find what's the limiting reactant. So at this point, I'm going to clean it up a little bit and make the question look like what I would call an ideal or maybe even simple problem in stoichiometry. So the question we want to ask is, what volume of water would I get from 12.5 moles of N2H4? So I would set it up like this. How many liters of water is equal to 12.5 moles? And because I have moles of one material, I can use the coefficients from the balanced chemical equation. 2 moles of N2H4 will produce 4 moles of water. And I'm going to go ahead and put those in. 2 moles and 4 moles, so that my moles of N2H4 up here and down here cancel. At this point, I have moles of water. Now, if I assumed we're at STP, my next step would be to say 1 mole of water is 22.4 liters. And I could have an answer at this point. That's technically not correct because water's a solid at STP, so it's not possible. So maybe the better way to do it would be ignore the fact that it says produced at STP, and let's ignore the 22.4 liters, and instead, and you can see if we did that, we get an answer of 560 liters. But instead, I like to rework the problem, and this time work it maybe the correct way. So we would say, as before, 2 moles of N2H4 produce 4 moles of water, and we'll put that in so that moles of N2H4 cancel out. Our next step would be to say 1 mole of water has a mass of 18 grams. Recall, oxygen weighs 16 grams per mole, and each hydrogen weighs 1, so there's 2 of those. So that adds up to 18 grams per mole. Moles of water cancel, and now I have to remember the density of water. You probably know it as 1 gram per milliliter. So I'm going to use that fact that 1 gram of water has a volume of 1 milliliter. That's the density of water that your teacher probably reminded you of earlier in the school year. Grams of water cancel. Now, I could leave my answer here, but it's in milliliters. We were asked to come up with a volume in liters, so now I have to remember the conversion, that metric conversion between milliliters and liters. And hopefully you recall 1,000 milliliters of water is equal to 1 liter, so that milliliters of water cancel. And now I get the actual answer that you would get for this problem if you were to do it in the lab. Excuse me. And that's 0.45 liters of water, far different than the 560 liters we calculated earlier. Let's go on to the next part of this question. Okay. The next part we want to answer is, well, let's see if it comes up here. Not sure what was going on there. That still looks like an A to me. Sorry. Let's get to B. There we go. How about find the number of liters of nitrogen gas? So we want to know the volume of nitrogen gas produced at standard temperature and pressure, assuming the reaction goes to completion. Now, because we figured out earlier that when we went through this math, we got the 12.5 moles of N2H4, and we got the 9.78 moles of N2O4, and then we divided by the coefficients for each. We found the smaller number was the limiting reactant, so that N2H4 was the limiting. So again, I'm going to use the 12.5 moles of N2H4 to solve for my answer. So let's see what that would look like. What volume of nitrogen is equal to 12.5 moles? So very quickly, we could use the coefficients. 2 moles of N2H4 will produce 3 moles of nitrogen. Making the units cancel, because I have moles of N2H4 up here, I need moles of N2H4 down here. So from the balanced chemical equation, we were told 2 moles of N2H4 will produce 3 moles of N2. Notice the moles of N2H4 cancel. If I stop now, I'd be at moles of N2, and I want to get to volume or liters, so I need another conversion. Now this is where, if we assume the nitrogen is at standard temperature and pressure, because that's what it says in the question, it's okay to say 1 mole of nitrogen gas occupies 22.4 liters. All gases occupy 22.4 liters, that is 1 mole of them, at standard temperature and pressure. So the moles of nitrogen cancel, and when I type this into my calculator, I will get the answer of 420 liters of nitrogen. Okay? Let's see what comes up next. How about this one? Find the mass of excess reactant left over at the conclusion of the reaction. Now this is one that seems hard, but it's really not too bad. If we go through our initial step, we found that, well, let me slow it down here. We know that the N2H4 is limiting. So I calculated several times here that the moles of N2H4 is 12.5 moles. Now, if I look at just the coefficients, for every 2 N2H4, I notice there's 1 N2O4. So what I'm going to do is calculate how much N2O4 I actually need. So based on the coefficients, if this is 12.5 moles and there's a 2-to-1 ratio, I probably need half that number of moles, or 6.25 moles of N2O4. Once I do that, I can multiply by the molar mass of N2O4. Each mole of N2O4 weighs 92 grams. So that means I need 575 grams of N2O4. Now, we were told that I have 900 grams. So if I take the difference between those two, 900 grams minus 575 grams, I'll get the 325 grams that is left excess reactant. The other way to do this is what I'm showing on the bottom. I'm just going to calculate the amount, the grams of N2O4 that I need based on the moles of limiting reactant. So how many grams of N2O4 do I need from 12.5 moles of N2H4? So it's going to be the same as what I've done above, but it might look slightly different. We know from the equation 2 moles of N2H4 react with 1 mole of N2O4. So I'm going to fill that in right down here, 2 moles of N2H4, and then right up here, 1 mole of N2O4. I get that again from the balanced chemical equation. Moles of N2H4 cancel, and at this point I'm left with moles of N2O4. If I did the math here, I'd actually get 6.25 moles. My last step is to show that 1 mole of N2O4, now I have to calculate the molar mass. 4 oxygens at 16 is 64 grams, 2 nitrogens at 14 is 28 grams, so that has a molar mass of 92 grams per mole. Moles of N2O4 will cancel, and that means that I will need 575 grams of N2O4. And as was given in the original question, the 400 grams of N2H4 was limiting. That means it's all used up. And we had, at the beginning, 900 grams of N2O4. So if I take the 900 grams I have and subtract the 575 grams I need, the difference of that is 325 grams of excess or unreacted N2O4. All right, let's look at that second question, number 6. So we have our balanced chemical equation, and in this first one we want to find the number of moles of sodium oxide. So this is the sodium, this is the oxygen, so that makes this one the sodium oxide. Find the number of moles of sodium oxide produced if you have 100 grams of sodium and you have 60 grams of oxygen. Now, don't be fooled by just looking at the coefficients. We have to convert these to moles. Sodium weighs 23 grams per mole. That's the molar mass from the periodic table. 100 grams divided by 23 grams means that I have 4.35 moles of sodium. For oxygen, what will I have to divide by? If you said 32 grams per mole, you're correct. 60 grams of oxygen given divided by its molar mass of 32 grams will give me 1.875 moles of O2. The next step, if you recall, is to divide each of these by the coefficient in the balanced chemical equation. So the 4.35 moles of sodium, I will divide by the number 4, the coefficient in front of sodium, to get 1.087. The oxygen, I will have to divide this one by the number 1, the understood coefficient in front of oxygen, and I'll get 1.875. The smaller of these two numbers, the 1.087, indicates that sodium metal is the limiting reactant, and therefore 4.35 moles of sodium is the amount that I will have to be able to calculate the moles of sodium oxide. So I would focus on just the moles of limiting reactant, and then we'll make the problem look like a traditional mole-to-mole calculation. So this should have just one step. I'm trying to find how many moles of sodium oxide are there in 4.35 moles of sodium. That was the equivalent of my 100 grams of sodium. So I can use the coefficients from the balanced chemical equation. 4 moles of sodium will produce 2 moles of sodium oxide. So I put this in so that the moles of sodium go in the denominator. In the numerator, I have my 2 moles of sodium oxide. Moles of sodium cancel, and I just plug that into my calculator, and I get the answer, 2.17 moles of sodium oxide. Let's look at part B for this question. Part B says, find the mass of excess reactant left over. Well, we just did one like this, if you recall, and we said what we could do. We know we have 100 grams of sodium. We're going to use all of that up because that was our limiting reactant. And so what we really need to do is just find out how much oxygen we'll need and subtract it from the amount that was given. So how much I need would be X grams. So I'll set this up. Now I have my 100 grams of sodium divided by the molar mass of sodium, 23 grams per mole. That's where I got my 4.35 moles of sodium. Now there's a 4:1 ratio. So I simply took this number, 4.35 moles of sodium, divided by 4. That's where I got my 1.087 moles of O2. And then to go back up, I multiply by the molar mass of oxygen, 32 grams per mole. And I get 34.8 grams of oxygen. If I wanted it the more traditional way, I would say how many grams of oxygen equals 4.35 moles. I would set up my first conversion factor to say 4 moles of sodium on the bottom will react with 1 mole of oxygen on the top. Moles of sodium will cancel. If I stop now, this answer would be 1.087 moles of oxygen. Okay, I'm doing the same thing going around this little square here. My next step would be to say 1 mole of oxygen has a molar mass of 32 grams, so moles of oxygen cancel, and I'll get my answer, 34.8 grams of oxygen. That's what I need. Now, we were told in the problem we have 60 grams of oxygen. 60 grams right here. We're going to need 34.8 grams. So if you subtract that from the 60 grams, you will have 25.2 grams of oxygen excess or left over. Pretty cool, huh? Let's try part C.